Okay, let's get started. In this quick video, we cover two key concepts, completeness and compactness. As far as the first one is considered, completeness is key in applications. For instance, in dynamic programming, we seek the solutions in various forms, with various forms of iteration processes. We do these iterations in some normed vector spaces in the hope of finding a solution in the same space, in the same normed vector space. And in order that we have the solution in the same vector space, this vector space, the vector space in which we work, is supposed to be complete. In the previous lecture, we have already covered the definition of complete normed vector spaces. If every Cauchy sequence in a normed space has its limit in the same space, then the space is complete. This was just a kind reminder. A complete normed space is often called a Banach space, but we want to extend this definition to subsets. As we will see in the next lecture, we will use the definition of complete subsets in the proof of the projection theorem, which is key. So at the end of the day, we need the definition of complete subsets. We have an obvious candidate definition. We can define completeness of subsets in the same way as we defined complete normed spaces. If every Cauchy sequence in a subset of a normed space has its limit in the given subset, then the subset is complete. That's all to that. But as we will see in Theorem 1, completeness can be defined in terms of closure. So a subset of a Banach space is complete if and only if it is closed. In other words, if we have a Banach space and if we have a subset, a closed subset, in this Banach space, then the subset is complete. And in addition, theorem 2 claims that in a normed linear space, any finite-dimensional subspace is complete. The other key concept or definition we cover now is compactness. Again, this is key in dynamic programming. For instance, please go back to theorem 4.6 of the Stokely-Lucas textbook. It claims that the feasibility set must be compact, which is ensured in assumption 4.3, in order that the value function iteration has a unique fixed point. So among other preconditions, if this condition of the compactness of the feasibility set is met, then we have a unique value function at the end of the iteration process. So why is it important to us in maximization problems in general? In many cases, we want to maximize a functional over a set or subset, and we want to know if a minimum or a maximum exists. In many cases, in simpler cases, the basic form of the Weierstrass theorem helps, but we must distinguish between finite and infinite dimension spaces. In finite dimension, in general, this is the n-dimension Euclidean space where n is finite. So in finite dimension, we say that a set is compact if it is closed and bounded. Practically, it means that there are no missing points in the set. So this is the reason why we say the set must be closed, because if a set is closed, there is no missing endpoints, and there must be no missing points in the set. In this case, there are no punctures and missing endpoints. In this case, the set is compact. In such a case, in such finite problems, the basic Weierstrass theorem ensures that the continuous that a continuous functional interpreted over a compact set has an extremum, minimum, or a maximum. So to see existence, we only need to show compactness and the continuity of the functional. This result, the Weierstrass theorem, can be generalized to cover infinite-dimensional problems, but in this case we need two other definitions. We need to redefine continuity. Actually, we replace it with another definition, and we need to redefine compactness too. So to generalize the Weierstrass theorem to infinite-dimensional problems, cases, we replace continuity with upper semi-continuity. You can see the formal definition, which we can easily interpret by saying that we can approach, we have a functional, and we can get arbitrarily close to the value of the function at x0 from above by reducing the difference between x and x0. This is very similar to continuity. So this is the way how we define upper semi-continuity. We can reverse this definition to define lower semi-continuity, and if a functional is both upper semi-continuous and lower semi-continuous, it is continuous. But to generalize the Weierstrass theorem to infinite dimension cases, more precisely put, if we want to generalize, reformulate the Weierstrass theorem in a general way, which can be applied to infinite dimension cases, we only need upper semi-continuity. And the other definition we need is compactness. A set in a norm space is compact if, given any arbitrary sequence in the set, there is a subsequence that converges to a point, to an element, to a vector in the same set. In many cases we use, just please remember the course Recursive Economic Dynamics. In many cases we use the reverse of this definition. If we know if a set is compact, then it must have a subsequence that converges to a point, to an element in the same set. And if we, now that we have upper semi-continuity and compactness, then we can restate the Weierstrass theorem. An upper semi-continuous functional defined over a compact subset of a normed linear space achieves a maximum over this compact subset. So to see existence, we need to show if a functional is upper semi-continuous and if the set is subset is compact.